We'll wait like 1 more minute for people to join, and then we can start. Okay, I think we'll start now.
Okay. Uh, Shoot. Give me a second. Okay.
I think while Lucas figures that out, I guess we can introduce ourselves. So I'm Shamik. Uh, I've qualified for the AME and NAC. I know physics, and my hobbies are reading books and Latin.
Oh yeah. Hi guys, I'm Lucas. I also made Amy, and uh, I my team won the Bibalashvili Award at the USA Youth Physics Tournament. I also know physics, and I like to do basketball and running. Uh, so I like you guys, all of you, to please turn on your camera if you guys can. If you guys have like a working camera, if not, um. that's okay, but we really prefer to be able to see our face and see your reaction to what we say, and it will allow us to communicate more effectively. So if you guys could turn on your camera, that would be great. And while that's happening, I'll ask everyone to introduce themselves. Um, how about Jacob? Do you want to go first? Introduce yourself.
Uh, I guess so. My name is Jacob. Uh, I guess I like math. Any questions you have, or
No, that's fine.
oh, okay.
Yeah. Uh, how about Adrian? Do you want to introduce yourself? Um, Maybe
Uh,
share a fun fact.
Hi, My name is Adrian, and a fun fact for myself is that my family's from Puerto Rico.
Nice. Also, what grade are you in, and what's your favorite physics topic? That'd be really cool if you could share that.
Yeah, yeah. I'm a junior, grade 11, and one of my favorite topics in physics is fluids.
Nice. Yeah, that's a very good choice. Fluids is pretty cool. Um, Jap, do you want to go ahead and introduce yourself? Where you're from, what grade you're in, and what's your favorite physics topic?
I think his audio is not working. That's fine. We can move on to a different
Hey,
person.
that's fine, yeah. How about Tamid? Am I saying your name correctly?
It's Tamid.
Tamid, okay, yeah.
Yeah.
Where are you from? What grade you're in, and what's your favorite physics topic?
Yeah. So I'm from Tennessee. And I I I'm in 10th grade. Um, and my favorite physics topic is probably energy and work probably. Uh, and was there anything else?
Yeah, that's it. Yeah, that's good.
Yeah.
Yeah. Um, wait, what about, oh, I think someone left, but all right, that's it. Right. It's great to know all of you guys. And yeah, so let's move on to the next slide. Yeah, so this is basically our overall class structure. So we're gonna start every class by reviewing the homework from last week. This week we don't have any homework, but I mean like we don't have any homework to go over, but after today's class, we're gonna like email you guys the homework. And even though it's not mandatory, we really strongly recommend you guys to at least look over the problems and do what you can to like make an effort to solve the problems. And if you guys have any questions or you guys have like solutions to the problems, feel free to like, just write it up on a piece of paper, or you can also write it on overleaf if you want and email it to us, and we'll try to give you feedback or like hints as soon as possible. Our class will be mostly lecturing, but we're also going to have like problems for you guys to reinforce the concepts. Now, our classes will be from 1 p.m. to 2:30 p.m. PDT or PST on Saturdays, and then our class will last 2 months. Yeah, and if you guys can, again, it would be great if you guys could turn on your videos, but oh yeah, I see Adrian has this video on. That's really, really good. Um, if you guys, if the rest of you could do the same, that would be really nice. And also, uh, like don't be afraid to ask questions because if you don't understand something, that probably means like other people in the class don't understand it. So it'll help both you and other people in the class. Like, don't feel ashamed, okay?
And if you don't want to ask questions out loud, you can always message me or Lucas. Yeah.
Yeah, you can also use the chat. Yeah, that's really helpful. Yeah. All our syllabus. Um, this is actually we're gonna actually slightly modify the syllabus to a 10-week syllabus, but this is basically overall what the concepts are in electromagnetism. Like all you need to know for um USFO and the AP Physics C exam or AP Physics 2 exam. And if you guys can, make sure you join our Discord channel. You can just click, or I don't know if you guys can click that link, but you can write it down and then join the Discord like after the class and make sure you join our class channel. There's a specific channel in the Discord where we're gonna like communicate with you guys. So make sure you join that. And yeah. So today we're gonna be talking about charge and current and also electrostatics. So let's start with charge and current. So what is a charge, right? So a charge, we can say it's either positive or negative, okay? And then basically every particle, like we have things called, like we have particles, right? And then they will have a positive or a negative charge, and then it's quantized. So like you can have you can have like some particles have more charge than others, and it's sort of like mass, right? Because um you can have like, for example, 10 kilograms of mass, or you can have 100 kilograms of mass, and you'll soon see that we can also have like different quantities of mass, right? The difference between mass and charge is that we have one difference is that we can have positive and negative charges, and we see them in everyday life. But for mass, we usually only see positive mass, okay? And also, we have that opposite charges attract each other while like charges repel. So if I have a positive charge and a positive charge, then they will repel. And if I have a negative charge and a negative charge, they'll also repel. And if I have a positive charge and a negative charge, those two charges will be attracted towards each other. We usually denote charge by letter Q, and its units is coulombs. And so I can have a particle that has 10 coulombs of charge, or like 20 coulombs of charge, or 100 coulombs of charge. Oops. And yeah. Um, and you might have heard of these terms before, like proton and electron. Um, these they have the amount of charge they have is 1.6 to times 10 to the negative 19th coulombs. Or you can express it in microcoulombs, right? That'll be 1.6 times 10 to the negative 13th coulombs. Do you guys have any questions? If not, I'll just move on then. All right, so like this is Coulomb's law. Okay, so it's really similar to the law of gravitation. Let me see if I can annotate right now. Give me a second. Or give me a second, guys. I'm gonna try to figure how to annotate. Sorry about that. And yes, we'll be emailing you guys the slide, and we'll send it into Discord. I guess I can't make this work out, but yeah, I'll just restart sharing the screen. Okay, so we have Coulomb's law, right? It's similar to the law of gravitation. Uh, the law of gravitation, right? We have F equals big G, and then you multiply the two masses together and you divide by the distance between the two masses, the center of masses of the two masses squared, right? And in Coulomb's law, it's really similar to that. So if you have two charged particles, right? Like two charges, then there's going to be like either an attractive or a repulsive force between the two. Okay. Now, similar to the law of gravitation, instead of K, we have G, big G. Sorry, instead of big G in the law of gravitation, we have K, and K is approximately 9 times 10 to the ninth newtons meter squared per coulomb squared. And here, Q1 and Q2, they're the charges, they're the charges, like they're the amount of charge that the two particles have. And it's similar to like, you have the amount of mass that each like M1 and M2, right? And then R, it's the distance between the two charges. So if Q1 and Q2, um, again, if Q1 and Q2, they're the same sign, then, uh, Hamid, would there be attraction or repulsion if Q1 and Q2 are the same sign?
So if they're the same sign, they're probably attraction.
Yeah, so actually they'll be repelling. Remember, if we have two charges, then they have opposite signs, then they're actually gonna attract. And if they have
Or
same
like
signs,
oh
they're gonna repel. Yeah,
like the okay.
yeah. Yeah, don't worry, we're all learning. So yeah. Do you guys have any questions? If not, I'll just move on then. Wait, so here's the problem. If particle A has a charge of 0.3 coulombs and particle B has a charge of negative 0.2 coulombs and they're separated by 30 meters, find the magnitude and direction of the force acting on particle A. And remember, if you guys need this, K is 9 times 10 to the ninth newtons meters squared per coulomb squared. I'll give you guys a few minutes to work on this. And if you guys have an answer, just send it in the chat to either me or Shamik.
Make sure not to send it to everybody.
If you guys are stuck on anything, just message us and we can try to help you. Okay, Adrian, do you want to tell us your solution and how you did the problem?
Hi. I use Coulomb's law. So then first with the Coulomb's constant, 9 times 10 to the power 9. And then you look like the charges, which is 0.3 coulomb to 0.2 coulombs. So only the magnitude of that is going to affect the strength of the force, I think. So 0.3 times 0.2 and divided by the radius squared. So divided by 30 squared. And then because you look at the sign to see the direction of the force, so because it's opposite sign, you know the forces are going to point inward to each other. They're going to point towards each other. And then by Newton's first law, I think it's going to be equal and opposite force on each system.
Yeah, a really good solution. So, just to recap what Adrian said. Okay. So, yeah, so the force between the two, right? We have the force, by Coulomb's law, right? It's K times, and then you do the product between the two charges, you divide by the distance squared, right? So here K would be 9 times 10 to the ninth newtons meter squared per coulomb squared. And your Q1 would be like 0.3 coulombs, and your Q2 would be negative 0.2 coulombs. And then you divide by the radius squared, which would be 30 meters, and then you square that. And you'll get 6 times 10, around 6 times 10 to the fifth newtons. And then the part about which direction the force is acting on particle A. So you know that because they're opposite charge, particle A and particle B, they have opposite charges. So you know they'll be attracted towards each other. The so the force on particle A would be pointing towards particle B, and the force on particle B would be pointing towards particle A. And yeah, so you know that the direction of the force acting on particle A would be towards particle B. And Adrian, you said he was talking about Newton's first law, but I think what you meant to say is Newton's third law. Um, but I get what you're saying, and it's really good intuition you have. So um the the force on particle A, that's equal and opposite to the force on particle B. And yeah, very good intuition. And yeah, the final answer we get is 6 times 10 to the fifth newtons, and direction is towards the right. Uh, does anyone have any questions about that? Feel free to ask. Okay, let's just move on then. Here's another problem. Find the force due to a dipole, which is two charges, Q and negative Q, a distance 2d apart, at a distance z away from its center. And what I mean z away from the center is, let me, oh, come on. So that just means, oh man, I can't annotate, but distance z away from center. Imagine, um, if you imagine the line that's perpendicular to, like if you have a line connecting the two charges, uh, and you draw a line that's perpendicular to that line, and it's like it goes right through the center of the dipole, then um, if that's a distance z away from the horizontal line, then what will the force be? Uh, yeah.
Also in the diagram, like you can see like field lines. You can ignore those for now. We'll talk about those later.
Yeah, so it'll be a perpendicular distance z from the center. Yeah. Thank you, Jacob. Okay, I'm gonna stop sharing for a second just so that I can solve this technical issue. Yeah, and when I mean at distance z away from the center, so what I mean is uh wait, shoot. If I'm looking at a point over here, then that means that this distance over here, uh this over here would be z. Okay, yeah, and if you guys are stuck, here's a hint. So remember when we were doing Coulomb's law, right? We want to find the distance between like some point and a charge, right? And here we know that for example, if I want to find the distance to this negative charge, you can draw this Let me use a different color. Uh, I'll use red, right? So you can draw this triangle over here, right? And it's a right triangle, and they're a distance 2D apart. So yeah, so this over here would be D, and this would be Z, right? And now I want to find this distance, right? So how can you find uh that distance to the charge in terms of D and Z? And then try doing that. Okay, I'll give you guys one more minute and then we'll go over it. Okay, guys, you guys are all getting really, really close to the answer, but for time's sake, I'll just start going over it. So let's clear all the annotations. So we want to find the force due to a dipole at a distance z away from the center. So what it means is if I place a test charge here, so like call it QT, okay, or yeah, QT, and then I want to find the force on QT due to this negative charge over here and this positive charge over here. So remember, we have Coulomb's law, right? F equals to uh, K, Q1, Q2 divided by R squared, right? And then here, let's just qualitatively look at the forces, right? So QT, if we assume it to be positive, which in conventionally we say that QT is a very, very small um, positive charge. So there's going to be an attractive force pointing towards the negative charge, if I draw it like that. And let's say F plus. And there's also going to be a repulsion force from the positive charge pointing in this direction, right? Uh, F, oh, sorry. This will be F plus, and this will be, that'll be F minus, okay? Now we want to find F plus and F minus, right? The magnitudes. So F plus, right? F plus, that'll be K, and then we multiply the two charges together, right? So this has charge Q, and so it'll be QT times Q, right? And then divided by R squared, right? But what is this R squared? This R squared, you guys initially were saying it was D squared, but that's actually not correct because the R squared is the distance between the charge and like the test charge and the positive charge. So it's this distance, right? And then let me switch a color. So if we want to find that distance, right? We know that this is D and this is that vertical distance is Z, right? So we have a triangle. We have a right triangle. And from Pythagorean theorem, you know that this length over here, right? That will be square root of D squared plus Z squared, right? So that's our radius R, right? And then divided by R squared, so it will be D squared plus Z squared. Do you guys have any questions right now? Let me check. Yeah, if you have any questions, just send them in the chat. Should I square Q? No. So, uh, when we're finding the force between two charges, we multiply the two charges together, right? And right now, uh, this charge QT is not the same as this charge over here. We don't know that, so we'll just say it's QT times Q. Yeah, good question. If you guys have any other questions, let me or Shamik know. Okay. Uh, if you guys don't have any questions, then I'll move on. Okay, so we found F plus, right? And you know that because like the magnitude of F minus, right? That'll be the same because like the two charges, even though this one's negative and this one's positive, right? Um, their magnitudes will be the same. So if I do the absolute value of the force, the absolute value of F plus, that will be the same as absolute value of F minus, right? Uh, yeah, so we know that F plus and F minus, these two vectors over here, let me clear it. Okay, I'll redraw it. So we have over here QT. So we have F plus over here and F minus over here. Their two magnitudes are the same. But remember that force is a vector, right? So when we're adding, like the total force that the test charge experiences would be the vector sum of these two forces, right? So total F would be, right, that'll be F plus, that's a vector, uh, and then plus F minus, right? Yeah. And you know that the vertical components of these two vectors, they'll all cancel out. And like, you know, if I decompose these two vectors, uh, let's see. You see that these two vertical components, they cancel out, right? So when I do this sum over here, I'm actually only taking the horizontal component of both force, right? And how do I find the horizontal component of both force? So you know that if I draw, I'll redraw the original triangle over here. So the horizontal component of the force, right? I want to find the cosine of this angle over here, right? And if I do some geometry, like it's the same as this angle over here. That's also theta. And what is cosine theta? Well, cosine theta, cosine theta, that's just d over square root of d squared plus z squared, right? Shoot, sorry. Okay. And then our the net force F, right? The magnitude of F, which is our net force, that will be, that's two like F plus magnitude, which is the same as two of the magnitude of F minus, and then times cosine theta, right? But we also know cosine theta that's the same thing as d over square root of d squared plus z squared, right? So if you do the algebra and you work it out, right, you're gonna get a final answer of, I believe, 2k qt times q divided by, right, we have d squared plus z squared times square root of d squared plus z squared, right? So that would be uh d squared plus z squared to the 3/2 power, and then, right, yeah, and then times d, and that should be our final answer. Yeah. Uh, Wait, I know this was a bit like, this might have been difficult to understand. So let me check the chat for some questions. Are we placing a test charge of charge plus 1c at a point z above the midline?
The
Okay,
test charge has any magnitude. It's
yeah,
just denote it QT.
yeah, we don't need to explicitly know the magnitude of qt. We just keep it as like qt when we calculate it. Yeah, the force, these two, the only force these two charges, there. Oh, okay. So yeah, so right now in this problem, we're not trying to find the force between these two charges. We're we're assuming that these two charges are fixed, so there's like some external agent keeping them from like being from like just colliding into each other, and we're just looking at, if you have a test charge over here, uh, like at a perpendicular distance z from them, then what will be the force that test charge experiences? But good question. Uh, if you guys have any other questions, make sure to ask them, because this was a bit of a tricky problem. Okay, then I will. Oh, wait, are there such things as electric dipoles? Yes, there are such things as electric dipoles. Electric dipole, all that is just, if I have. Wait, I'll just clear the screen for you guys. An electric dipole is, all I need is I have a positive charge particle and a negative charge particle, and we just call that an electric dipole. And then in like an object, uh, like in any object you have in real life, it's just composed. Like if I have a box over here, if you zoom in really, really close, you'll just see particles that are like, you'll have, like if you zoom in really close, you'll see that there's a positively charged particle and there's a negatively charged particle, and they're like next to each other. Because like if because objects like all objects are made of electric dipoles. Yeah. So yes, there are such things as electric dipoles. But that was a good question. Yeah. Any other questions? Just feel free to put them in the chat or email us after class if you want. Wait, then I'll move on. Okay. Shamik, you want to explain Bohr's model?
Yeah. So basically, you might have seen this in any chemistry class you've taken. Uh, this is Bohr's model of the atom. Like they got it through a lot of experimentation and they built upon the works of like past scientists. So they obtained like this model, which is basically you have a nucleus and there's protons, which are positively charged particles, and you have neutrons. So they're just condensed into this nucleus. And then you have this big electron cloud of electrons, which kind of like in a sense, like they orbit around nucleus, and the electrons orbit in like certain shells. So it's kind of like the planets orbiting the sun in a way, but there can be multiple electrons in each shell, and yeah, so they're orbiting around in these shells, and we call the outermost electrons as the valence electrons, and they're very important in chemical reactions, but that's not really necessary for E and M. And while this model isn't like fully correct, and you can explore why that is on your own, uh we're gonna use this for any problems related to this. So yeah.
Yeah, very good explanation. Yeah, so you don't really need to. This is just some like background knowledge that it's good to keep in mind, but like just specific stuff about Bohr's model, like it won't be tested on like any usually won't be tested on like physics competitions or the AP. So don't be too stressed about knowing this part. But yeah, let's talk about current now. So you might have heard of current, like you have a circuit and then there's like some sort of current. So now we're gonna like actually define what current is. So when you have charges that are moving through a region, there's going to be a current, and current is just like you have a flow of charge. Um, the units is amperes, which is 1 coulomb per second, and we define it as like if you have just like an area like you have an area A that charges are moving through, then you define that current through that area would be the amount of charges that move through per second. So that's why it has a unit of coulomb per second. And we can also define J, which is our current density, which is the amount of charge flowing per unit time per unit area. So it's just the current I divided by the area A equals to your J. Um, Conductors, they can have current while insulators cannot, and that's just because we say that conductors you can have charges that can freely move through, while insulators the charges cannot freely move through. So if charges can freely move through, then you can surely have a current. Yeah.
Some examples of conductors would be like just your typical metals like copper and stuff.
Mhm. Yeah. Yeah. And okay, I see a question about what is wrong with the fluid flow analogy for current. Uh, Wait, Adrian, can you elaborate more on what do you mean by the fluid flow analogy?
Hello?
That's an interesting
Um,
question.
yeah, it was like in my class too, like we were talking about current and it was like they thought they thought like with like water flowing through a pipe, if it was going faster, then it'll be higher current. So the velocity of the charges is related to the current or directly proportional to it. But like they thought like it the analogy sort of broke down when like you thought of current like constrictions in the pipe. So and I just like thought like or just need clarification on that because like where that analogy broke down to.
So yeah, okay, that's a good question. Uh, okay, so you're talking about I think you're mentioning when the pipe, like have you have fluid flowing through a pipe, and when the pipe, like the cross-sectional area that like decreases, right? Is that what you're talking about?
Yeah.
Okay, yeah, I get what you're saying. So yeah, so if you guys don't know, so like you have like there's a thing called the continuity equation where basically if you have a fluid flowing through a tube, right? Then you need to have like to maintain that the amount of fluid here that moves through is the amount of fluid that moves through here per second, right? So that like you're not losing any fluid, right? Like there's a thing called a continuity equation where like A1 V1 equals to A2 V2, right? Right. And then uh so like if this cross-sectional area, let me draw it better. So if we have the cross-sectional area here is this is A1 and this is A2, right? So this equation means that here if the fluid's if all the fluid is moving at some velocity v, right? Then over here, when it's a smaller area, right, you'll get a bigger velocity of the fluid, right? So the fluid's velocity would increase when you're getting to a region that's like smaller cross-sectional area. And the reason why like I think what you're mentioning is like this fluid model breaking down is that if you have a wire and yeah, if you have a wire and like just say has a it has some certain cross-sectional area here and some cross-sectional area here, um like you have charges moving through right over here. Just because the wire has a smaller cross-sectional area doesn't mean that the velocity of the charges will increase, because the reason why we have the continuity equation for fluids is that fluids cannot be compressible. But the thing is, for charges, like you can have charges like maybe they're like spread out like this, as they're moving through. And then when it goes through a narrower section of the wire, they'll like be more clumped together, right? Like this is totally allowed. So it doesn't mean that the velocity of the charges have to increase when it goes through a narrower section of the wire. It only applies to fluids because fluids cannot be compressible. So essentially, like basically the density of the fluids, it cannot change. But whereas if we had charges moving through a wire, their density is allowed to change. So the velocity will not necessarily change when we move through a smaller, a narrower section of the wire. Does that make sense? I think that's what your teacher was referring to about like breakdown of the model. Adrian, does that make sense? Or uh
Yeah, thank you.
yeah. Let's wait, there's some more questions. Is there any other more intuitive way to describe current? Seems kind of weird to define current as the amount of charges. Oh wait, what if the charges are different? What if the areas are changing? Oh wait, this is a really good question. So what if the charges are different? So when we're let me clear the screen first. Okay, when we're talking about current, right? It's we have charge moving through a specific area. Like say that's our wire, right? Uh okay, so hypothetically, I guess what you're saying is hypothetically, if we have like charges of different values, like for example, I have one charge here and maybe it's like 2 coulombs, and I have a different charge here. It's maybe only 1 coulomb and it's moving through a wire. Although usually this doesn't happen, but um just hypothetically say it happens. This is an example where I think you're saying the charges are different. But when we say current, it's just the net amount of charge that moves through. So if both of these, like after 1 second, they all move through uh that like that like area, that cross-sectional area, then the total charge that moves through it's 3 coulombs, and our current will be 3 coulombs per second. So even if the charges are that are moving through, they have different like magnitudes of charges, uh, all we care about is the net amount of charge that moves through our like the the section of area we're investigating. So yeah. Uh, what if the areas are changing? Good question. Uh, yeah, so if the areas are changing, so usually this doesn't happen in real life, but if the areas are changing, then I mean, what that will do is that'll just change. Hold on. Yeah, that'll just change the like the denominator, right? We have chart like oh wait, shoot. Like if the areas are changing, but our the amount of charge that goes through and the yeah, if the amount of charge that goes through stays the same, then our current stays the same. The only difference is when we write J equals to like the current divided by the area, right? If our area is changing, but our current stays the same, then that means the current density is changing, but the area the current will stay the same. That's actually a really good question that you pose. Uh, Conservation of charge. Yes. Yes. Very good, Adrian. Yeah. So the amount of charge that moves through the wire has to stay the same. So our current stays the same, but the current density would change because our area is changing. Yeah. All right. So if there are no more questions, um, eh, if there are no more questions, I'll just go over the example. So this should be quick. Every 3 seconds, 2,000 electrons pass by a point in the wire. What is the current at that point in the wire? Um, I'll just go over it for time's sake because we're running a bit low on time. So we want the current will be 2000. Uh this is our total charge and divided by 3 seconds, right? And then E would be the magnitude of the charge of the electron, right? So a common mistake would just be to write I would be equal to 2000, sorry, 2000 divided by 3 seconds, but that's wrong because remember, the charge of an electron is not 1 coulomb. It's actually 1.6 times 10 to the 19th coulomb. So the actual answer would be 2000 times 1.6 times 10 to the negative 19th divided by 3, and our unit is ampere. So yeah. And if an electron is traveling to the right, which way is the current generated by that electron? Sorry, there should be a negative here. Wait, which way is the current generated by the electron? So this is also a really good question that you guys, and like, it's really helpful to keep this in mind. If we have a negative charge, right? It's an electron, right? So it's moving this way. Remember, the current will be the total charge, like through some point divided by the amount of time that passed, right? And if our total charge, right, because it's an electron, our current is negative. So it's as if you have a current going towards, like, you can sort of like think of it as a current going to the right, but it's a negative current. So isn't that the same thing as if you have a current going towards the left and it's positive current? So maybe a better way to think of this for you guys would be if you have a negative charge and it's moving towards the right, it's the same thing as if you have a positive charge and it's moving towards the left, right? So then if it's a positive charge moving towards the left, then the current will be towards the left. Just remember, the direction of the current is always the direction that the positive charges are going, not the negative charges are going. You always have to keep that in mind. So if I have a negative charge moving towards the right, it's equivalent to a positive charge moving towards the left. So our current is pointing towards the left. Yeah. Do you guys have any questions about that? Just like drop a message in the chat. Yeah. It seems like everyone's good, so I'll just move on. Uh yeah. Yeah, so remember we need to multiply by this 1.6 times 10 to the 19th coulombs divided by yes, because that's the charge of the electron, and towards the left because current is the movement of positive charge. Okay. electric field. So electric field, uh, so first thing about electric field, right? If we have a charge over here, like, or just you can look at this diagram over here, right? So if we have an electric charge here and it's positive, right? The direction of the field line is the direction of the electric field. And so to think about this, imagine you place a test charge here, okay, QT. The direction of the electric field will be the direction where the test charge would move towards. So here, the test charge, right? They're both positive. The test charge and this charge over here, they're both positive. So test charge will be repelled this way. And that'll be the direction of the field line. And the density of field lines is proportional to the strength of the field. So if I draw, if I draw this is my positive charge. And if this is the field line of, looks like that, it's kind of not that dense. If this is one positive charge, okay, and this is another positive charge, then let's see. How about, okay, Jacob, can you tell me, um, if I'm comparing, shoot, like Jacob, if I'm comparing this positive charge versus this positive charge, if you judge based on only their electric field lines, uh which charge has like a greater magnitude? Like which particle has greater amount of charge? If you just
Uh,
yeah.
Probably the one with more field lines.
Yeah, because it's a denser field lines, right? So it's a stronger strength of the field, so uh the magnitude of the charge will be greater. So yeah. Lines come out of positive charges and go into negative charges. And that's just because uh if I have a positive charge and I place a test charge somewhere, then it'll be repelled, right? So the lines will go like outwards because like the test charge is repelled away from the positive charge. And if I have a negative charge, right? Then if I place a test charge, like say I put a test charge here, it will be attracted towards the negative charge. And this is what the field lines between a positive charge and a negative charge look like. Because you see, if I place a positive charge, like a test charge over here, you can see it'll be repelled by the positive charge and it'll be attracted by the negative charge. So if I place it here, it'll eventually just crash into the negative charge. But if I place a test charge over here, right, then it'll be repelled this way by the positive charge, and there will be a small attraction from the negative charge, but this attraction is not strong enough. Well, I think, let me see. So for this one, the attraction will be strong enough so that uh the test charge will move along this path and it will eventually go back to negative charge. But if it starts over here, right, the attraction from the positive charge will be too big. Like it'll be like the attraction from the negative charge will be much greater, much less than the repulsion from the positive charge. So this uh this if I put a test charge here, it will just like escape to infinity. Yeah. Let's move on. Yeah, so electric field lines, they give us the direction, but what is the magnitude of the electric field? Well, so the electric field, we have E equals KQ over R squared. Notice this is just like it's almost like our formula for like the Coulomb force, right? You had F equals KQ Q1 times Q2 divided by R squared. This time there's only one charge Q, right? And you have like F will be equal to like some charge and then times the electric field at the point where this charge is. Okay. And then yeah, remember that the electric field it's a vector, and yeah, make sure it's a vector. And also, you should know that electric field lines, they can never cross because the electric field it always gives it's always like a unique direction. So if I have wait, just ignore the example for now. If I have like two field lines, electric field lines, and they cross, what this implies is that at this crossing point, electric field points both in this direction and also in this direction, but that can't happen because the direction of electric field is unique. So yeah, make sure that when you draw your field lines, they never cross. Uh, right, draw the electric field lines for the following space containing two protons. Uh, yeah, so I'll just draw it right now for time's sake. Um, so if I place maybe a charge here, right? It'll be repelled, like a test charge here. You would imagine that it will be repelled by the positive charge on the left, like this way, right? But also be repelled by this positive charge over here. So there will be like it'll it'll be smaller, but it will be pointing in that direction. And Adrian, can you tell me why repulsion the force due to this positive charge will be greater than the force due to this positive charge if I'm looking over here, and assume that the two positive charges have the same amount of charge.
Uh, if the if the if they're the same magnitude of charge,
Yeah,
then wouldn't it if it was if the positive test charge feels the repulsion from the closer charge more because it's squared, so like it
yeah,
weighs that closer side more, so it's
yeah,
gonna have like a stronger force.
yeah. Good, good, good. So remember, the force is divided by r squared, right? If I have a smaller r, then that means like force is proportional to 1 over r squared, right? So if I have a smaller distance to the charge, then there will be a greater force, right? So this repulsion force will be greater than this repulsion force. So initially, the test charge might travel in this direction, right? But we'll get to a point where the repulsion from this positive charge uh like as it gets closer to the positive charge on the right, there'll be more and more of this repulsion like away from the positive charge. So you'd expect it to curve like this way, and then eventually it'll just curve away towards infinity, right? So if I draw the field lines, it'll look, or I'll go to the next slide. Yeah, so it'll look like that. So the initially a test charge might go in this direction, but as it gets closer to this chart over here, it'll start getting repelled more and more, and it'll start curving away or curving upwards. And the same thing on the right side. Okay, this problem we can skip it because all you have to do is just apply that like E equals E due to each of the charges will be K times the charge divided by the distance squared. So yeah, there's not really yeah, I'll just skip that problem for now.
You can do it as extra homework if you want.
Yeah, you can do it just for extra practice. Uh Shamik, are you taking over from here or
Sure.
okay. Yeah, I'll let you yeah.
Okay. So we have Gauss's law in E&M. This is one of the most important laws that you're gonna meet, so you should probably like fully understand this one. So we have to first introduce flux. So flux is kind of like how many electric field lines are going through a defined area, and you can basically write that as integral E dot ds. If you don't know calculus, that's fine. Basically, integral is like you're taking each like a very small area over the whole area, and then you're taking the electric field at that point, and you're dotting those two vectors, and then you're just like taking that over the whole surface, and that gives you your flux. keep in mind that the vector for each area is normal to the area. So if this is my area, my vector would point up. And what Gauss basically said is that this flux is actually equal simply to the enclosed charge over the permittivity of air. The permittivity of air is just like a constant. It's like 8.85 times 10 to the negative 12 or something. And enclosed charge is basically how much charge is enclosed within the surface you have defined. So in the diagram, you can see like there's a sphere is the Gaussian surface. Um, you can see the E dot ds. That'll give you your flux. And the enclosed charge, there's just that like one positive charge inside. So that's your only enclosed charge. If you had like one positive charge and one negative charge, both with magnitude q, the enclosed charge would be q plus negative q. So if you had a wait, uh, if you had a q and a negative q, then your enclosed charge would be zero because you just add them. So yeah, and this is very useful in a lot of symmetries. So yeah, so usually you're gonna see spherical cylindrical symmetries. For example, if you had a line of charge, as here, if you just had like a line of charge, just like infinite basically, and it had a certain like charge per length, like charge was evenly spaced along that rod, then you would define your Gaussian surface as a cylinder. So in that cylinder, uh, your E would always be pointing up from the rod. It'd just be pointing up here, down here. And your A vector, area vector along the cylinder will be pointing up here in the side kind of. And in the bases, it'll be pointing to the left and to the right. And you can see that E dot dA in the bases will be zero because they're at a 90-degree angle. But E dot dA along I guess, I don't know what it's called. It's like the side. We'll just call it the side. E dot dA along the side it's like non-zero. You can calculate this. And then and then you can calculate the enclosed charge here because you know lambda is charge per unit length. You know the length of it. So Q enclosed would be, wait, can somebody tell me what Q enclosed would be? Uh, Adrian.
Hello.
Uh,
The Q enclosed of the cylinder,
yes.
the that'd be like the linear charge density times the length.
Yeah, good job. Does everybody get that with this line of charge example? I don't see any questions. So you can do a similar thing for a lot of other like configurations. Usually you want to take either a sphere, a cylinder, uh, yeah, those are pretty much the two main ones that you want to take as your Gaussian surface. Next slide. Lucas, next slide. Oh yeah. Um, Show that the value k has the same value as 1 over 4 pi epsilon. We can skip this for now. You can do this on your own. It's pretty interesting. Your k in the Coulomb's law will be equal to 1 over 4 pi epsilon naught, like the permittivity of air thing. Yeah. So next slide. Okay, I think these are more practice problems. You can do these. We can do the challenge question right now, I think. This one is about Gauss's law, so it'll be good practice. If you don't want to do the graph, that's fine. At least derive an expression for the electric field. You guys, as a hint, this like long, solid, non-conducting cylinder is very similar to the infinite rod that I just explained. Okay, I think we'll go over it now. So basically, you want to take your Gaussian surface as a cylinder within the cylinder you have right now, because you want to find electric field at a radius r less than r. So like let's take this, right? This has radius r, and then we can write Gauss's law. So integral E dot dA equals Q enclosed. And by the way, if you're planning to take the AP Physics C, E, and M or something like that, you will need to like show your work. So you'll need to write this step down. Make sure not to skip steps. But anyways, so to find Q enclosed, we're given uniform volume density rho. So it's rho times what the volume of this. Volume of this is pi r squared. Oh yeah, I forgot to mention this is length L. Pi r squared L, right? And uh this can be written as simply E times A, where A is the surface area of the side, because as I told you before, the E dot dA of the bases, like those circles, will cancel out. So we only look at the surface area of the side. So E times A equals rho pi r squared L over E naught. And A, can somebody tell me what A is quickly? Anybody?
For the A, like the integral of dA, is it 2 pi r, well, 2 pi little r times the length?
Yeah, good job. And I think Alan also said that. Yeah, so 2 pi small r L. And you can like do algebra, you'll get E. You get, if you want to know, you get rho times R over 2 epsilon naught for A. So any questions on A so far? Uh, okay, I don't think there's any questions, so I'll do part B now. Uh, so for part B, we want radius R greater than R. So we basically do the same thing. We're gonna take a cylinder that is coaxial with this, and we'll like put it so mm, this is R, and again we have this L. So we do the same thing, right? Integral E dA equals Q enclosed over E naught. And this is different from A in that your Q enclosed is rho times V, but your V, wait, I'll write down. Q equals rho times V. In part A, our V was um pi r squared times pi little r squared times L. Here, it's not gonna be pi small r squared times small r squared times L because we only have charge up till this big R. Like this stuff, like there's like no charge in there. So like it'll be rho times pi big R squared times L, it will be the enclosed charge. Um and A A will just be still be 2 pi small r L, right? This like side surface area of this. And you can do same algebra because this is still E times A. You can do your algebra. You get you should get rho r squared over 2 epsilon naught r. So any questions on that? Okay, so I'll go over part 3 now, part C. So on the axis below, sketch the graph, right? So, actually, this is B. Uh, A was rho r over 2 epsilon naught. Uh, rho r over 2 epsilon naught. So we can see that for A, this is proportional to small r, and for B, it's proportional to 1 over r, small r, 1 over small r. So we can just like draw it. So at small r equals 0, our expression from A will give us 0 as E is 0, which makes sense, right? Um, and at r small r equals big R, you'll have um, rho big R over 2 epsilon naught. You can see that both the expressions of A and B will agree at big R, and that's good for like validating your answer. Um, and we know that's linear, so that's just linear. And then from there, it's proportional to 1 over R, so it'll be like that kind of. Uh, and it'll be asymptotic to this, right? Hopefully that makes sense. Are there any questions about that one? Uh, okay. I think our time is done. So thank you for coming. I think we'll send the slides by email and the homework also. Uh, yeah, okay. Bye.